Welcome back. Today we're diving into a seriously fascinating explainer. We're looking at a groundbreaking paper published back in May 2026 by Guo and their team. Now, if you follow AI, you already know that training large language models to do exactly what we want, it's incredibly resource intensive. Honestly, it's a massive balancing act. Well, this research introduces a framework called DVAO, that's Dynamic Variance-adaptive Advantage Optimization. And it's a real game changer because it directly tackles one of the biggest bottlenecks in AI training today. Let's unpack exactly how this works. So here's the fundamental challenge we're facing. How do we fix training instability while teaching an AI multiple complex goals all at once? You see, when we train these models, we aren't just teaching them to be smart. We're teaching them to be helpful, to be harmless, to follow strict formatting rules, and to use tools correctly. Those are all totally different goals, or rewards in AI terms. But here's the catch. Forcing a model to learn all of these distinct things simultaneously, it often completely breaks the learning process, causing it to spiral into pure instability. This explainer is all about how the DVAO team finally solved this core tension.
Real quick, here's our roadmap for today. We'll start with aligning large language models, then we'll look at the multi-reward problem. After that, we're introducing DVAO, breaking down exactly how it adapts dynamically, and finally, we'll wrap up with the benchmarks and results. All right, let's jump in.
Section 1. Aligning large language models. This is our foundation. Okay, so to really grasp the problem, we need to quickly touch on the baseline of modern AI. Reinforcement learning, or RL, is basically the gold standard paradigm for aligning LLMs with human intent and task requirements. Imagine treating the AI like it's navigating a giant maze. We give it signals, rewards, whenever it gets closer to what we actually want. Without this foundation, an LLM is literally just a highly sophisticated autocomplete. Reinforcement learning is the secret sauce that makes it a genuinely usable, helpful assistant. And you know, AI training has evolved incredibly fast. For a long time, Proximal Policy Optimization, or PPO, was the reigning champion. But PPO is heavy. It requires a whole separate value model just to guide the training, which eats up massive amounts of memory. So the field naturally evolved toward Group Relative Policy Optimization, or GRPO. GRPO is our current, incredibly efficient, value model-free alternative. It saves both memory and compute. But as great as GRPO is, adapting it to complex real-world scenarios brings up a pretty massive hurdle.
Which brings us to Section 2, the multi-reward problem. This is what happens when objectives collide. In the real world, you almost never have just one reward. You want your AI to be great at math, sure, but it also needs to be polite and concise. Currently, developers try to merge these competing goals in two pretty flawed ways. First, there's reward combination. You basically just add all the rewards together. The problem? When you do that, the mathematical values assigned to these goals multiply out of control. It generates advantages with excessively large squared magnitudes. In plain English, the numbers absolutely explode, and the AI's training becomes wildly unstable. Then, on the flip side, we have advantage combination. This tries to play it safer, but it relies on static hyperparameters. It's just way too rigid and completely ignores how different objectives correlate or even conflict with one another. So yeah, neither of these standard practices actually works well for multi-reward settings.
So, let's move to Section 3, introducing DVAO, the dynamic solution. Now, take a look at this quote directly from the paper. It is the absolute heart of this explainer. It says, DVAO dynamically adjusts combination weights based on the empirical reward variance of each objective, effectively upweighting objectives with a stronger learning signal while suppressing noisy ones. Think of DVAO like a world-class orchestra conductor. Instead of just forcing every single instrument to play at the exact same volume, which, let's face it, just creates a wall of chaotic noise, the conductor dynamically listens. When a clear, strong melody is playing, DVAO turns that volume up. But when there's static or confusing noise coming from a specific reward, it dials it back. It literally finds the clear radio station amidst all the static, and it does the whole shebang in real time. Moving right along to Section 4. How DVAO adapts dynamically, the mechanism. Let's break this mechanism down, because it's brilliantly systemic. First up, DVAO evaluates objectives within what's called a rollout group. That's basically just a batch of the AI's recent attempts at a task. Second, it calculates the empirical reward variance for each of those objectives. It's peeking under the hood at the math to see which rewards are bouncing all over the place and which ones are staying stable. Third, it dynamically adjusts the combination weights based on that variance. And finally, step 4, it applies those weights to upweight the strong learning signals and suppress the noisy ones. Because this process is self-adaptive and happening constantly, it entirely prevents that explosive instability we were just talking about with the older methods.
Let's hit Section 5, Benchmarks and Results. The proof.
So, the big question, does the theory actually hold up? Well, the data shows that DVAO isn't just some clever workaround, it's mathematically rock solid. The researchers mathematically proved that DVAO maintains bounded advantage magnitudes. What this means for us is guaranteed order and stable training. The numbers literally cannot explode anymore. It also introduces a self-adaptive cross-objective regularization mechanism. But honestly, the real star of the show here is that it achieves a superior multi-objective Pareto frontier. Basically, the AI doesn't have to sacrifice its performance on one task just to get better at another. It pushes the absolute boundary of what the model can achieve simultaneously, demonstrating incredibly robust training stability over all the baseline methods.
And I love this part, they didn't just test this on tiny toy models in a lab, they completely grounded this framework in reality. The team ran extensive experiments using serious, state-of-the-art models like Qwen3 and Qwen2.5. They threw highly complex tasks at them, specifically evaluating them on rigorous mathematical reasoning benchmarks and advanced tool use benchmarks. Now, these are exactly the kinds of tasks where multi-reward instability usually just ruins everything. But DVAO, it held strong, significantly outperforming those standard practices across the board. Which leaves us with a pretty fascinating final thought. With training stability finally solved from multi-reward settings, what complex tasks will AI master next? Think about it. By removing the bottleneck of explosive magnitudes and rigid, static rules, Guoqiao Zhang and this research team have essentially taken the training wheels off. AI can now learn to juggle multiple, highly complex objectives fluidly and dynamically. It's a massive, massive leap forward from model alignment. Thank you so much for joining me for today's explainer. I really hope this look into DVAO helped clear up the incredible math happening behind the scenes of AI's rapid evolution. Keep learning, and I'll catch you in the next one.